In this video, I'm going to explain how to set up a phase field fracture simulation, so a failure analysis of a defect in a pipeline. This can be coupled to hydrogen diffusion and degradation, and the initial results of the results of the welding model can be used as an initial input. To keep the same geometry, it's again easiest to just copy the previous model, and let's call it fracture. And we want to change a few things in the geometry, mainly or only in the partition of the geometry. So we're going to analyze a crack in this simulation. So what we want to do is want to actually draw the crack in our geometry, which we can just, well, let's say we have a straight crack, we can just here create a line, say from there to there, and let's say this is the crack that we have and that we want to examine. And what I advise to do is to create a small region somewhere in the pipe at the bottom here, in the center of the pipe, where we can basically determine the hoop stress and convert that to internal pressure while we're doing our simulation. So I'm going to create a small section over here. In the center over there. Okay, that's the partition. Then you want to check if all the relevant sets are still assigned correctly. So I want to have one set which is just the full pipeline. This one. We don't need separate sets for the base and weld metal over here, so we can delete those. These are what we're gonna assign coarse edge sheets. And the fine edge sheets in this region over here. Around the crack, we want to have a much finer mesh. Let's also create a set for the crack. And finally, one where we measure the hoop stress. Then let's create the material. We still have a material over here. We can actually change this. So the current fracture simulation needs state-dependent, solution-dependent state variables, 11. We don't need expansion and a user material like this. Okay. We still should have a section assigned with the right material. Let's check if this. Yep. So the section is still assigned. Then next, let's take a look at the loading steps. Let's delete all the steps that were in there from the previous model. Okay. And let's create a new step. We basically need only one step. Okay, you can also make two steps. Then in a small step where you apply the crack, and then in the second step where you apply the loading. But it also works in one step. So let's create a step, and we're gonna very slowly load the pipeline to let the hydrogen diffuse through the pipeline. So we take in seconds a very long time period, and let's choose some initial or maximum steps. And finally, something you want to do over here, or you might want to do over here, is choose the solution technique. So for the fracture model, most of the times the quasi-Newton method converges better in my experience. Sometimes the full Newton converges better. But my advice is to try it with the quasi-Newton first and just keep this number of iterations allowed before the kernel matrix is performed to the default value of 8. If you encounter convergence issues, you can either play with this number or try to see if the full Newton method works. But let's choose a quasi-Newton method for now. Okay. And then another thing you want to do in steps is to go to the menu above over here, go to other and general solution controls. And we want to edit some settings in the solution controls in our step. Abacus gives you a warning that these are advanced parameters, but we need to set those. And basically, why we need to set those is that because in a fracture simulation, in increments where crack propagation occurs, convergence usually takes place after a few hundred iterations. And Abacus, already way before that, thinks your solution is not converging and aborts the increment and cuts the time step. So we want to avoid that. The way to do that is go to time incrementation over there, specify what we want to do in these steps, and set this to a very high number, such as 2000. And then also go to more over here and set these to 2000. If you want to know what these actually mean, you can go to the Abacus documentation online, where it is explained. But usually set everything to 2000, like the first ones. And then I usually set this IG to a somewhat lower number. This basically tells Abacus if my time increment convergence has converged within this amount of increments, then I try to increase the time step again. So this usually works for me. Now what we also want to do is to click on line search control over here and put the line search number, which in default is usually, because I've probably enabled quasi-Newton, it automatically says here 5. You can put this a little bit higher. So with the regular Newton method, this is 0, but we want to enable line search control over here. Then we want to prescribe the binary conditions. So we want to prescribe a pressure, but what we're actually going to do is going to prescribe the radial displacement on the inner surface of the pipeline, and using the formula for Denwald cylinders to relate that to a pressure. So that's this formula over here. And another thing we want to prescribe later on is the hydrogen concentration, which you can also relate to the pressure you want to prescribe, given over here. I linearly want to prescribe the pressure in the pipeline right now over the very long time period that we have specified. So basically what we need to do in Abacus is to create amplitudes which basically prescribe the displacement and the hydrogen concentration over time. So I've used basically a target pressure that I want to pre-describe, and I've created, you can calculate basically these formulas over here. You can create a table in Excel first, or in any other programming or scripting language that you want. And especially for the hydrogen concentration, this is needed because if we linearly increase our pressure over time, the hydrogen concentration that we want to prescribe to the inner surface of the pipeline does not need to increase linearly. The radial displacement actually does. So I want to, let's go to Abacus, create an amplitude, and let's call this displacement amplitude. And here we can define a table basically. So this is the simulation time, and this is the amplitude that you want to describe at that time. So for the pressure that I want to reach, for the displacement, we can just use 2 data points basically, because the displacement was a linear function of our pressure. So at the final simulation time, I want to reach this displacement. And here I've just chosen a large enough pressure, large enough displacement, so that our pipeline is definitely going to fail. And the simulation will abort earlier if the pipeline has already failed. And I want to create similarly an amplitude for the hydrogen as a function of time. And this one has much more data points because it's not a linear relation. So we're gonna create a table over here. Then we're actually gonna prescribe the boundary conditions. Let's check what boundary conditions are already in there. Yeah, let's just delete them both and create new ones. So let's first create the radial displacement. So let's call this displacement in step 1, and it's a displacement rotation. And let's create a set, select all the edges where you want to apply the displacement. It's basically on the inner surface of the pipeline. Make sure you don't select the excess raw material over here, because that's going to lead to stress concentrations if you form this in the same way as this edge. Just select the inner edge of the pipeline over there. Let's give this set a name. Let's this. Okay, and we want to prescribe a radial displacement. And the way to do this is that to basically do not use the global coordinate system over here. But actually, okay, one over there. Let's create a new coordinate system. So we want to create a cylindrical coordinate system. Cylindrical over here, and then it asks you to select a point, which is the origin, which is the center of the pipeline, and 0, 0, or in this case, a point on the radial axis, which I'm going to specify as 1, 0, 0, so pointing in this direction. And then on the arc theta plane, which is then 0, 1, 0. So we've now created a cylindrical coordinate system, and gonna select that one. And now actually our displacements are applied in this coordinate system. So U1 over here is radial displacement, and we want to set that to 1 and choose the displacement amplitude that we've chosen. So now this 1 gets multiplied by the displacement amplitude at a given time. So actually the displacement is fully prescribed by the amplitude that we defined over there. We also, now you apply an outer displacement, but to make sure that rigid body motion is constrained, you also want to constrain in at least one point the radial displacement. So we can do it in the same way. So fix radial. Let's choose point over there. It's called fix radial. And that is the U2 direction. And this is what we will just want to set to 0. Okay. Then the hydrogen boundary conditions. So we want to create a hydrogen boundary condition on the inner surface of the pipeline. And actually to prescribe this, we cannot select directly hydrogen because it's not an available degree of freedom in Abacus. But with some post-processing scripts that I provide with the code, the easiest thing to do is to prescribe the hydrogen as a electric potential over here. So let's select electric potential. Let's select everywhere we want to apply this boundary condition. So that's again the inner surface of the pipe. And in this case, we do want to select the boundary over here. The magnitude again equal to 1, and let's choose now the hydrogen amplitude. And finally, we also want to apply a hydrogen concentration to the outer surface of the pipeline. Again, an electric potential. And let's select the entire outer surface. And this one we want to set to 0 because there's no hydrogen on the outside of the pipeline. Then there's one final boundary condition that we need to apply, and that's actually the crack itself. So we want to set basically the order parameter of the phase field model to 1 on the crack over here. So let's create another boundary condition. And similar as with hydrogen, there's initially no degree of freedom for the order parameter in Abacus. But the easiest thing to do, and then which will later be automatically converted with the pre-processing scripts, is to choose the crack, prescribe that as a mechanical rotation actually. Let's call this crack. Displacement rotation, let's select the crack, although we also made a part crack over there. So it should be that one. And so that's going to be UR3 over here, which is usually a rotation. But since we don't have rotation degrees of freedom in our model, we're going to prescribe the crack over here. So let's set that to 1. And we want to have the crack prescribe that 1 immediately at the start of our simulation. So let's choose the constant amplitude over there. Okay. We still need to mesh to create a mesh for our geometry. Let's go to mesh. Let's delete all the seeds that are in there, which are messed up now because we changed the geometry. Okay, and let's create some new seeds. So we have already selected the coarse lines. Let's give that a coarse seed, and then we get the finer region in the around the weld and around the crack. Should be this one now. And let's give that a much smaller seed. So let's say 0.1. The advice is to base this on the length scale parameter that you're using in the phase field model. As a rule of thumb, it's good to have 5 elements within a length, phase field length scale. So if you have a phase field length scale of 0.5, then element size of 0.1 should be good enough. Okay. Let's check what kind of element types that we are having in the whole geometry. We want to have plane strain elements of quadratic order with reduced integration selected for the quadrilateral elements over there. And let's finally check also the mesh controls to make sure that we only have quad elements in our mesh. Okay, so I want to set this to quad only. Let's finally create some global seeds where it's good to set the approximate global size to the coarse seed size that we've prescribed, which was 2, and the absolute value of the minimum size to the finest seeds that we have prescribed, which was 0.1 in this case. And then mesh the geometry. So this should give us a quite coarse mesh around the region where a crack is located, or a quite fine mesh, I mean, and a much coarser mesh everywhere else. And the final thing you want to do in the Abacus user interface is to specify what output we want. As these models get quite large, you can basically choose to not write the output out on every increment. Let's say on evenly spaced time intervals. Let's create those 50. We don't want to write out stresses because that's handled as a state-dependent variable. Same thing with strains. We do want to keep displacements. Let's then select these. And we definitely want to select here the solution-dependent state variables. Okay. Something else that we can do is we can create, for example, another output. Let's call this pressure. So if you want to keep track of the pressure in a pipeline, the actual pressure in a pipeline during the simulation, and we want to write this out in more than the 50 time steps I just specified for the general output. What you can do is here select a set, and we have created the hoop element over there, and we want to write out the solutions dependent state variables for that element, and let's choose, let's say, 200 evenly spaced time intervals over there. Okay. You can now write the output file. So let's go to jobs, create a new job again, which we call fracture in this case. Model fracture, okay. Okay. And let's write the inputs. Okay, so now it gives an error, which basically the error over here is that the radial displacement that we have is not applied in the same coordinate system as the angular displacement. So we forgot to select the correct cylindrical system over there. Okay. And this should, of course, not be radial, but let's call it angular. Okay, let's check if it works now. Yep, so now the input file is written. So we should have, if I go to my working directory, a file fractured temp over here. That was one thing I forgot to do before writing the input file. We still had these predefined fields defined coming from the mechanical simulation that we copied. So we need to delete these, otherwise Abacus starts complaining that it cannot find these fields. So let's delete these and write the input file again. Next, we want to change this file so we can use it with the subroutines that are provided. I've provided a Abacus Python script for this, which is called fracture input.py. Needs to be run in a similar way as the input files for the thermal and mechanical simulations. So let's copy the command over there. Let's go to the command prompt in our working directory. So the command that we need is Abacus Python and the script, then the name of the input file we just created, and here we need to specify either a 0 or a 1. And basically what this does is 0 prepares the input file to run a simulation without hydrogen diffusion, and 1 with hydrogen diffusion. So now we want to include hydrogen diffusion in simulation, so we need to set this to 1. And this should have created a new file, which is called fracture, and then what is appended is mesh h. And there are a few things that should have been changed over here. First of all, the definition of our user element should have been inserted, which is over here. Basically tells you that we're going to use a user element with the degrees of freedom 1 and 2, which are displacement degrees of freedom, 3, which is written as a crack, or the order parameter of the phase field model, and 7 is the hydrogen concentration. Next, it is also inserted these user elements, and what it has done is that the elements that were initially ordered 1 to the number of elements that we had are basically appended after these user elements over here, and these elements are actually needed for output, to write the output to the data to the output database that we can read into Abacus. It has also automatically renumbered the sets. So for each set that was already in the file, or each element set, it has created one new one with a -u for the user element, and one and change the numbering of the original element set. So that's basically the material that we specified, the UMOD material that we specified in the Abacus user interface. Still works, so we don't have to change anything over there. And as with the thermal and mechanical simulations, the names of the state-dependent solution variables, solution-dependent state variables are inserted. And finally, what we can see are the boundary conditions over here. And for these boundary conditions, the degree of freedom number 6, which we specified as the rotation degree of freedom, has now changed to 3, should be the crack, and the hydrogen concentration has changed to 7. Then we also need to create an input file specifying the properties, material properties. In this case, that one has to be called set parameters fracture.f90. So I've created this in the working directory that we can run a simulation in, and I've specified a few properties. So we have the elastic properties, which are the Young's modulus and the Poisson's ratio, the initial yield stress, the hardening exponent. These are elastic properties. In damage, so we can specify whether we want a strain split. So with 0 here, no strain split is applied, basically meaning that all the elastic energy contributes to damage, and 1 applies a hydrostatic deviatoric strain split, and that basically prevents the compressive stresses to contribute to damage. So then only hydrostatic and deviatoric stresses contribute to damage with 1. When I put 1 over there, we have our critical energy release rate, the length scale in our simulation or for the phase field model, and the beta parameter over here is what fraction of the plastic work contributes to damage. So you can say, if you put it to 0, only elastic energy contributes to damage. Put it to 1, the full plastic dissipation contributes to damage. But these we typically set to 0.1, basically meaning that 1% of the plastic dissipated energy contributes to damage, and your 90% is dissipated as heat. And these are the hydrogen degradation or the hydrogen parameters. So we have a diffusivity coefficient. This is a hydrogen degradation flag. It's basically, do we want the hydrogen to affect the degradation? So 0 is no degradation is applied, and 1 is the phenomenological degradation law that we use in the paper, and these are the parameters of that law. So for the degradation law itself, I refer you to the paper. And here I have created a parameter, which is not necessary, but you can put this one over there. And basically what this does is it aborts and makes sure that the simulation is aborted when the average maximum stress that is in the pipeline falls below the maximum average stress that over the whole time has occurred in the pipeline. So basically when the crack has almost fully propagated, then the simulation will abort. So we don't do additional increments, which do not make sense anymore and only cost us extra time. So with this file, we can now actually run the simulation with homogeneous properties. So we do not need additional input files. But what the simulation I want to do in this tutorial, we basically want to use the results of our previous weld model and use that as initial conditions in this simulation. So this requires an extra step. Another Python file is provided to basically prepare the properties to be read in by the simulation file. It's this script over here, fracture initial.py. Here you can see how to run it. Let's copy that and paste that to our command prompt. So again, Abacus Python and the script name. Then comes the database name. This is basically the results file that is obtained from the welding model. So the residual stress welding model. So that's the mechanical .odb file. And in the mechanical model, you need to make sure that if you go back to our Abacus user interface, that in the output files, basically you request for the solution dependent state variables, the stresses and strains, but also the predefined field variables, because the phase fractions are stored in here, and we're going to need those. So I forgot to do this last time, but I have done this, rerun the simulation in the meantime, so my results file has also the field variables in them. And I guess that one. Then we need to specify the input file that we just created for our fracture simulation. And note that in this case, basically the mesh does not have to be the same in the mechanical simulations as in our fracture simulation. So what this script does, it basically interpolates to a new mesh. So you can use either a finer mesh or a coarser mesh. You usually want a little bit finer mesh in your fracture simulation to resolve your length scale. And finally, what you can see over here is a text file which is called toughness data. This text file is optional. You can leave this out and it should still work. But what is specified in this toughness data file is basically the fracture properties which are dependent on the phase fractions. So these are in order to specify the property that we want to prescribe, so the critical energy release rate. This is for ferrite pearlite properties, and these properties are for bainite and martensite also. I haven't encountered martensite yet. And the same thing for the length scale, and these are the properties for the hydrogen degradation law and the diffusivity. These properties are not used in the residual stress or the mechanical simulation that we did before. That's why we have to specify them separately. If you don't do that, then these are not taken into account, but instead your simulation just takes these properties you specified here into account. So if we create this file, this should read in, and then I have probably made a typo here, toughness. Okay, and now a new file should be created, which has basically the name of the of our simulation input file, so fracture.inp over there, but then this initial behind it, so this one over there, and the structure of that file is as follows. Takes some time to load on my computer. Yeah, like this. So top row specifies the number of properties in this file. The next is here the number of elements, and this is the number of integration points per element. Then starts the definition of the first property. So this is the Q1 property, which is the parameter of our hydrogen degradation law. And then for each element and each integration point, we specify the property. So the properties are now specified for each integration point in our new mesh. You can specify, so now all the properties are in this file, but you can also create files which do not contain certain properties. You have to remove them, change the number of properties over there, and this should also still work. So it doesn't matter how much, whether you define all the properties in this file or just one, that should always work. Because what we have to do is here in the set parameter file, we have to specify that we want to use a property file, so specify it. This should be our path to the file. And what it does basically is all the properties that are specified in this file, it will override those properties that we specified here. So in this case, well, it overrides the critical energy release rate, but also the length scale and the yield stress. So basically everything that is in this file. So you don't have to specify it here anymore. But if you don't specify a certain property in the fracture initial file, you can specify it here, and then just the property is applied homogeneously throughout the material. That's everything that we needed to do. You should be able to run the simulation now. So let's open a command prompt. Just use the abacus command. Let's give it a job name. Then the input file is the input file that we have created with the adaptions in it. So that should be fracture mesh H. The user subroutine, or the file with user subroutines, is sim fracture .f90. Since these simulations are relatively big, can get relatively large, and we can also specify the number of CPUs that we want to use. So typically for the size of simulation that we're using now, up to 4 CPUs speeds up the simulation. After that, it saturates. So using more than 4 is usually not really beneficial. So let's use 4 right now, and keep it running in the command prompt. We use the interactive command again. So it's compiling now. Let's see if it starts running without problems. Yep. The simulation is finished. It actually says in the command prompt that abacus exited with errors, but that's because the user subroutine aborts when the crack is fully propagated, as we specified with this max load drop parameter over there. If you actually look in the fracture.sta file where the information about the increments is printed out, you can see that, well, in this time step it probably fully propagated the crack, and then it basically aborts the simulation over there. So we can go to abacus and open our results. See over there. Actually, few things what you want to do is, first you want to probably turn off or at least put it to a very low value deformation scale factor, and also let's not show the element edges like this. And then when you're using user elements, abacus will sometimes show this. You can turn it off by here, and I'm going to entity display, take off this bullet point, okay, like that. Yeah, so this is actually the propagated crack. You can see that we started out with the crack that we defined, and in the end this propagated like this. Yeah, so we applied our initial deformation, our initial conditions. So you see that it already had a lot of plasticity, which is coming from the welding simulation. You can see that it varies in yield stress over here. So if I show the plasticity, and then this is in the final state where the crack is propagated. has changed. So something else that we can do is try to plot the hoop stress. So I want to go to create XY data over there, to show the wave field output. And here we want to choose the S11, so that's the stress in the XX direction over here. And that's because we've defined the hoop element exactly at the bottom. This is, well, basically the hoop stress at the bottom of the pipeline. And we want to plot that in the element that we've created for that. So that should be the hoop element over there. So if I highlight this in the viewport, should be able to see it like there. It's in the middle of the pipe wall. Okay, we can save this, and we want to take the average in the element there. And we can plot that or export it. So here you can actually see the pressure buildup. A little bit of plasticity maybe globally, but not much globally. Everything happens locally, so you don't really see that in the global pressure curve. And then we get this pressure drop. So you can convert this, for example, to pressure by using the thin weld formulas.